Okay guys, today we're looking at rationalizing the denominator when it comes to simplifying square roots. Okay, so looking at our simplest radical form, we've covered the no perfect square factors, we've done no fractional radicands, and now we're on the no radicals in the denominator. Okay, so remember the denominator part of our fraction is always that bottom part. So what we first need to look at is we need to look at the property of multiplication. A times 1 equals A and 1 times A equals A. The reason this is important is because when we get to actually working with some of the problems here, we're going to be multiplying by something that is going to help us get that radical out of the denominator. Okay, and remember, anything divided by itself is just 1. Okay, so maybe this will make a little bit more sense once we look at some actual examples. But for instance, if I have like 2 divided by 2, that's really just 1. Okay, there's 2 things you're always allowed to do in math. One is you can multiply by 1, because anything multiplied by 1 is just itself, or add 0. Anything plus 0 is also just itself. Okay, so those are 2 things you're allowed to do in math because it doesn't really change anything. All right, so just keep that kind of property in mind. Conjugate expressions, if I have in parentheses a plus the square root of b and then a minus the square root of b, those are conjugate expressions. I kind of talked about that in one of the previous lessons and videos I recorded. Okay, the only difference between these two is this sign right here. One's a plus the square root of b, and the other is a minus the square root of b. These are called conjugates. Okay, we're going to notice that there's a pattern that happens with these conjugates, for instance, when we look at number 1. Okay, so when I look at number 1 in the warm-up down here, I have 4 plus the square root of 5 and 4 minus the square root of 5, okay? Well, when I do that, I'm going to FOIL those out, right? So 4 times 4 is 16. 4 times negative root 5 is negative 4 root 5. A positive root 5 times 4 is positive 4 root 5. And then a positive root 5 times a negative root 5 is negative root 25. So when I look at this, I notice I have some like terms already right here, negative 4 root 5 and 4 root 5. And when I combine those, they actually go away. So I end up with 16 minus 5. And of course, that 5 is coming from the square root of 25. And 16 minus 5 is 11. Okay, so multiplying with conjugates, I don't know if you guys remember me talking about it some earlier, but our middle terms kind of cancel out when we're working with conjugates. Okay, so for number 2, I have 10 minus the square root of 15 and 10 plus the square root of 15. Again, the only difference here is this sign. One's a positive, one's a negative. It doesn't matter what order they come in. Like, for instance, in number 1 and in the example, the plus sign's first and the minus sign second. And the second here, it's the minus sign's first and the plus sign second. I'm still going to go through and FOIL. 10 times 10 is 100. 10 times root 15 is positive 10 root 15. A negative root 15 times 10 is negative 10 root 15. And then, of course, negative root 15 times a positive root 15 is negative square root of 225. Okay, and again, we notice our middle terms are going to cancel out. And I get 100 minus 15, which is 85. Okay, so we notice that conjugate expression is going to happen a lot. We know that those middle terms are going to cancel out when we're foiling conjugates. Okay, that kind of stuff's important to remember because we might use some of that here in some of our examples. Okay, so what we need to do here is we need to write each number in simplest radical form by rationalizing the denominator. Okay, for number 1, I have 4 over the square root of 7. Okay, so not exactly like what we did last lesson, but we need to get that radical out of the denominator, right? That's one of our rules to get it as truly simplified as it can be. Okay, and I do that by multiplying by the square root of 7 over the square root of 7, okay? Remember, anything divided by itself is just 1. So this right here is coming from actually this identity property of multiplication where I'm multiplying by 1. Anything times 1 is just itself, right? Okay, so that's what I'm doing here. The reason I'm doing this, because watch what happens here when I do this. 4 times root 7 is going to be 4 root 7, but the square root of 7 times the square root of 7 is going to give me the square root of 49. All of a sudden, we notice that our denominator now has a perfect square in it. So we can take the square root of 49. So my simplest radical form here by rationalizing my denominator would be 4 root 7 over 7. Okay, so what we did there is we kind of seeked out how we can make this denominator a perfect square in order to get the radical sign or the radical entirely out of the denominator. But remember, if we're going to multiply by something in the bottom, it has to be the same at the top because the square root of 7 divided by the square root of 7 is just 1. And we are allowed to do that in math. We can multiply by 1 because it doesn't change anything. Okay? So, number 2, I have 4 root 5 over root 12. Here, I'm going to multiply the square root of 3. over the square root of 3. Now, we might be wondering, why are we choosing the square root of 3? Here's why. When I look at this, I'm going to end up with 4 root 15 up top, right? Remember when we did our multiplying lesson, we just multiply our coefficients. 4 times my coefficient of the square root of 3 is just 1. That's 4. And then the square root of 5 times the square root of 3 is root 15. Now, the reason I chose root 3 is because take a look at what 12 times 3 is. This is square root of 36, right? Okay, so the square root of 36 is a perfect square. And of course, we know the square root of 36 is 6. So I'd have 4 root 15 over 6. Okay, so we kind of want to try and seek out numbers that are going to be able to be multiplied by our denominator number, whatever it may be. Like, for instance, here we have the square root of 12 to get our perfect square in the denominator to be able to simplify it and get that radical out of it, okay? And of course, we can reduce this. We're not done yet, okay? 4 over 6 can reduce to 2/3. Remember, you always want to reduce your fraction if you can. They're both even numbers, so of course we can divide both of them by 2. 4 divided by 2 is 2, and 6 divided by 2 is 3. Okay, so there's the first two examples. Again, it's a little tricky, but I feel like once we maybe get the use or the hang of it, they won't be as tricky for us. So for this one, I have 7 over the square root of 27. Here I'm going to multiply the square root of 3 over the square root of 3. Again, we're going to see what's going to happen here when I multiply 27 by root 3. I'm going to end up with the square root of 81 in the denominator, which of course is a perfect square. So I get 7 root 3 over the square root of 81. Well, the square root of 81 is just 9. So I get 7 root 3 over 9. Okay, so that would be my most simplified form of that one because I can't reduce my coefficients anymore. Okay, for number 4, I have 3 root 2 over the square root of 50. Okay, square root of 50 here. This one might be a little easy to think about. Well, we're going to multiply by, I would think, 2. Root 2 over root 2 because 50 times 2 is 100. And we all know that 100 is a perfect square. So I have 3 root 2 times root 2, and I'm going to end up with 3 root 4 in the numerator all over 100. Well, notice what's going to happen in the numerator here, you guys. I have 3 times the square root of 4. Here I have a perfect square in the numerator and a perfect square in the denominator, but that's okay. So I'm going to get 3 times 2, because the square root of 4 is 2, over, well, the square root of 100, its perfect square is 10. So I have 3 times 2 over 10. So here I can just multiply my numerator. 3 times 2 is 6, 6 over 10. Hopefully, you guys are saying, well, we're not done yet. That can reduce. They're both even numbers. So I'm going to end up with 3/5. Okay, so a lot of this stuff right here is thinking, okay, what can I multiply my denominator by in order to get a perfect square in that denominator? Okay, and remember, we can only multiply by 1, so it has to be the same the denominator as the numerator, depending on what we're choosing for that spot. Okay, so a couple big takeaways here. What is the smallest radical you can multiply by what is the smallest radical you can multiply by to make the denominator rational? Okay, we want that perfect square in the denominator. So we need to multiply the numerator and denominator both by that answer. Okay, or you can multiply the numerator and denominator by the conjugate expression. So we actually didn't use too many conjugate stuff in those examples there, but that first checkbox is really where we hit hard. We need to find the smallest radical we can multiply that denominator by, and whatever we choose in order to get that perfect square, we need to put in our numerator too, in order to multiply the numerators as well. Okay, and that is it for today's lesson, guys.